So it is my great honour to have the distinct privilege of to being able to introduce our webinar today. So Dr. Petra Ágota Szilágyi, I hope I've got that quite close. Oh, perfect. Will be giving us the seminar today. So she is the recipient of a very prestigious Top 50 Women in Engineering Awards in 2000. She has travelled extensively across Europe, America, as far as Australia. She is a senior lecturer at Queen's Mary's University, and she heads up a group of advanced functional hybrid materials. And she will be speaking to us today about metal organic framework templates and hosts of nano catalysts. So without further ado, I will put the floor over to Dr. Szilágyi. And any questions that you have, please leave them in the Q&A section, and I'll read them out after this presentation.
Thank you, Matt, for the kind introduction, and also thank you very much for the invitation. It is a really big pleasure for me to be able to discuss my work with you today, and also hopefully this will be a little bit inspirational. I would like to start by saying that we are my group is mostly interested in designing, synthesizing, and characterizing new materials for particular applications, and catalysis is one of them. And hopefully you'll be interested in, we can find some ways of exploring these materials for different catalytic applications together. So I would just like to say that should you have any questions, I don't know how to move this. So if you have any questions after the presentation, just please drop me an email here. I think Corinne will also share this email afterwards. So I would just like to first position my research interest a little bit, and obviously we're all acutely aware of the current climate crisis, which is of course a consequence of anthropogenic carbon dioxide emissions or greenhouse gas emissions, and that is of course very strongly linked or closely linked with our industrial and so general human activities, including, of course, things that we talk a lot about, so such as transport and heating and cooling of buildings, for example, but it's really every single aspect of our lives that's involved, such as the production and processing of food, cooking, also industrial processes, particularly chemical industrial processes as well. And of course, it's very important that maybe not in the UK, but in very many countries, the production of potable drinking water is a very energy intensive process. And this is obviously very necessary for life. And we know that the reason for this is that globally, this energy demand is met by the combustion of fossil fuels. And we also know that this imminently has to be replaced by renewables. And so that is great so far, but this is, although a necessary requirement, it's not a sufficient one, because you would know also that renewable energy sources are also intermittent and unevenly distributed, both in space as well as in time. So also energy storage is necessary. So this is two major parts, I suppose, energy production and energy storage. At the same time, we also have to make sure that all the processes we use, all the industrial processes, both in the chemical industry as well as in heavy industries, we also try to make the processes more sort of atom economic or less energy demanding. And this is one of the major points my group is looking into. It is also very important to point out that for all of these aspects, we typically need to design new materials. And what we want is for these materials to not be more harmful than the processes we wish to replace them, replaced by them, such as, for example, their mining, processing shouldn't be more toxic or lead to more harmful consequences than the burning of fossil fuels. So this is what I call by the shifting of materials paradigm, as well as the shifting of the energy paradigm. And my group's interest is really sitting in the middle. So we're working with metal organic framework materials, and I will introduce them briefly in a moment. And we're trying to produce them using green chemical processes, and such as aqueous synthesis. And more recently, we also started to look into the upcycling of plastic waste and their conversion into metal organic frameworks directly. But perhaps more importantly, we're also exploiting these materials for energy and environmental applications. And the most important for the moment today of which is the catalytic processes. So this is both in order to develop more selective catalysts. So we would be then avoiding costly and energy demanding separation processes. But we had also looked at the production of synthetic fuels as well. This is not the only things we do. We also produce, for example, hydroxide ion conducting membranes for alkaline fuel cells. So that is for hydrogen cars. And we are also looking at developing solid state electrolytes for all solid state batteries. And more recently, we also started to look at thermoelectric metal organic frameworks. But today, I'd like to talk about metal organic frameworks for catalysis. So what are metal organic frameworks? And I'm sure that many of you had heard quite a lot of them. So I would just like to briefly summarize what they are, or review what they are, and perhaps emphasize a little bit what my interest in this kind of materials is. So they're a kind of hybrid material. They're made up of inorganic nodes. So these can be either metal cations or metal oxide-like clusters, which are interconnected by organic linkers, which can be typically polycarboxylates or heterocycles. And when these building blocks self-assemble, they form this extended three-dimensional structure, which are typically highly porous and highly crystalline. And this is really where my interest lies, because it should be pointed out that the pores themselves are part of the crystal structure. And as such, their size and shape is very well determined. So on the atomistic scale, really. So in a sense, we get these bits of emptiness, these pore spaces, which for catalysis, we mostly exploit for as a kind of a mode for growing catalyst nanoparticles and nanoclusters inside. And so we get to engineer the size of these particles and the shape of these particles very closely. And there are two different aspects, one of which I just mentioned. So this kind of a templating effect by the pores. That's one thing that in principle, we should have an atomistic level control on the particle shape and size that's grown inside the pore. But the other and perhaps even more important part or aspect of this is that, so I've already mentioned that these are hybrid materials. They have both inorganic and organic building blocks. So we essentially are tapping into both of these disciplines. And we would know that the geometry and the valency of both inorganic ions or clusters, as well as organic linkers, may be very diverse. And so when we are combining them, we can really unlock a huge multitude of different possible pore shapes and sizes. And yeah, so therefore we can really grow different kinds of particles in them. Apologies for the behind me. And the other aspect we are looking at is the surface chemistry. So particularly the organic part, but not exclusively, may bear all sorts of different functional groups in the framework. So as we're using it as a template and also as a part for gas clusters, these functional groups may interact to different extent with different strengths with the gas material. So we can tune this kind of host gas chemistry by choosing or selecting these different functional groups, and thereby we can finally, or so our hypothesis goes, that we can fine tune a little bit the surface electron density of these clusters. One more important thing I would like to point out is that the typical pore size of metal organic frameworks is between 0.5 and 3 nanometers. So it's really at the lower scale of nanoparticles and the higher end of nano clusters we're talking about. And I did mention that today I would be talking about how these can be used for catalysis. And of course, metal organic frameworks are solids. So we are interested, obviously, in heterogeneous catalysis. And as such, the surface is really important. And as I already mentioned, these metal organic frameworks are really highly porous. So they have surface areas of thousands of meters square per gram. And also, obviously, the pores themselves are very many and, once again, identical, basically, in shape and size. Excuse me. And so what we can do, we use it kind of in an inverse space as a mode to grow the nanocatalyst inside. And what that means that obviously we will increase the surface to volume ratio of these nanocatalyst guests inside the pores of MOFs, or maximize the proportion of surface atoms in them. Let me give you a concrete example of a metal organic framework, and this is the one that I will be talking the most about today. So this is the UI66. It's actually one of the most stable frameworks. It's built up of zirconia-like clusters. So these are hexanuclear zirconia clusters, which are interconnected by terephthalic acid. So this is one of the most stable frameworks, and it has two different kinds of pores. One of them is tetrahedral, and it's got 7.5 angstrom diameter, and the other one is octahedral, and its diameter is 12 angstrom in size. So if we say that, well, let's use this MOPOR, for example, as the template or the mold for the growth of our clusters, so we can think of maybe a metal cluster like this. So this is a palladium 17, so this is made up of 17 atoms, and it's 7 angstrom in diameter, so it should fit nicely and snugly inside the pores of this metal organic framework. But I should point out that this is really not the approach we're actually using to embed the metal inside the pores. We rather infuse a precursor of the metal of choice inside the pores, and then reduce it and allow the cluster to grow inside the pores of the metal organic framework. So yeah, this is the idea, that it really is a template, and so we would have a nice, at least in terms of the size of the cluster, we would replicate the size of the pores. And so at this size regime, so once again, I would just like to come back to this typical pore size regime for frameworks, so between 0.5 and 3 nanometers, we start to, so nanoscience really starts to kick in, and we would start to determine the properties of the particles to some extent by the particle size rather than by the constitution of the particle. And I think one of the very interesting questions, and I think it's also very relevant for catalysis, is to what extent the atomistic structure of the bulk crystallite can be preserved for such small nanoclusters. And I don't think that there is a very obvious answer to that. I mean, if you consider this 17 atom sized cluster, should we assume that the atomic arrangement in the cluster would be equivalent to, let's say, a cutout of a large bulk crystal containing 17 atoms? And I don't think that is necessarily an obvious yes or no answer. So we are very interested in exploring the atomistic structure of these clusters because, of course, that determines many of their properties. And we had developed this tool, the use of pair distribution function to determining what the atomistic structure of these clusters is. So in this case, we added palladium in MEL53. So this is an aluminum-based framework. And what we did is that, well, we assumed is the following. If we collect total scattering data on the empty framework and subtract it from the total scattering data of the palladium-laden framework, the difference curve we have should be basically a representation of the gas material in itself. So in this case, this is palladium. And this is what we got. So you have it in green. And what I would like you to focus on is really the data set in green at the moment. So the first thing that you should notice is that at higher interatomic distances, all we have is noise really. So the clusters are very small. And the second thing is that the positions themselves are very well determined. So this is actually, although I think whether it's crystalline or not is more of a question, or more of a philosophical question, because there is no periodicity really. But the atomistic structure is very well determined. And so what we did is we tried to fit the face-centered cubic crystal structure of the bulk palladium. And as you can see that the peak positions are a very good fit. And the problem is really with the intensity. And that is, of course, because the particle size is much smaller. And refining the model, we actually were able to determine that the typical particle size was around 7 angstrom. And that, in turn, allowed us to determine which of the 2 possible polymorphs of this framework is used as the template for the growth of the palladium nanoclusters in this case. But it's not only the physical properties of these of metals, for example, that change on this very low in the size regime, but also their chemical properties. And this is the next example I would like to discuss is about. And our motivation came from DFT calculations originally. It showed that for certain hydrogenation reactions on palladium and platinum, if there is a sufficient amount of subsurface hydrogen, it would significantly increase the reactivity of the hydrogen that is surface absorbed. And that is going through a kind of a destabilization of the surface hydrogen atoms through the subsurface hydrogens, because they change the electronic structure of the metal. And in the case of the palladium, it is very straightforward because under hydrogen, interstitial hydride may form. And this is something I will discuss a little more in detail. And not exclusively, but in particular for reactions where the dissociative chemisorption of hydrogen is the rate determining step, then we expect a huge change in the catalytic activity depending on the surface hydrogen concentration. And so what that means that the location and the concentration of hydrogen atoms in or on palladium actually matter a lot. We looked at this reaction. This is the selective hydrogenation of butadiene on palladium. So this is a well-known reaction. And so what we would want is to take the butadiene and we would only want to hydrogenate one of these double bonds. But what occurs often is that the palladium catalyst over-hydrogenates the reactant and the undesired butane is formed. And previously, it's been hypothesized that this is a consequence of the beta hydride formation of palladium. So this is actually the hydride phase, which has not only a high subsurface hydrogen concentration or abundance, but also the ability to replenish the subsurface locations for hydrogen from the bark. So this was hypothesized that the hydride phase is more active, whereas the metallic one is more selective. So I would just like to say a couple of words about hydrogenation, just to really disambiguate or clarify the terminology here. So if you have palladium, so it would be in the face-centered cubic phase. And if the hydrogen atmosphere is allowed on it, then the hydrogen molecules would be split into atoms, and the atoms would be able to diffuse into the bulk. And while the hydrogen pressure or the concentration is low enough, then this phase would remain. So this is the alpha, metallic, or solid solution phase. In fact, this tells it that it effectively behaves as a solid solution. So the physical properties of palladium remain the same. However, at a particular pressure at a given temperature, there would be a phase transformation in which the hydrogen would occupy the interstitial positions and the interstitial hydride would fall. So this is accompanied by a huge expansion of the lattice, as well as the change of the physical properties, such as it's no longer conducting and it's transparent, so it's not a shiny material, so it's no longer a metal. So this means that the phases affect the location and the concentration of hydrogen, and as we've seen, it's been hypothesized that those determine the catalytic performance. So the phase should be very crucial here. Further to that, the stability of the interstitial hydride with respect to the metallic phase depends on the particle size. And as you can see here, so about just below about 2.5 nanometers, the stability starts to, the interstitial hydride starts to be less stable when compared with the metallic phase for hydrogenation reactions. The hydrogenation or hydride formation. So it is quite logical to assume that at a certain size or below a certain size, the interstitial formation would no longer be thermodynamically favorable, and it would just simply not form. So this means that the particle size influences the phase stability and so the catalytic performance. And one more thing I'd like to point out, that all these different behaviors occur below or start to occur below 2.5 nanometer. And once again, I would just like to remind you that this is really much the pore size regime of metal organic frameworks. So if the palladium particles are small enough, then we could inhibit the interstitial hydride formation. And so we could verify the phase activity directly. So whether it's the hydride phase that is indeed the more active and less selective, or perhaps the other way around. And also, of course, we can use MOFs as templates to nanoconfine and anchor catalyst palladium particles in them. And so, of course, what we could do ideally is we would have all different sizes and see at what is the cutoff point where the hydride formation no longer occurs. Now, instead of that, we just went for a relatively safe option. And we went for this palladium 17 cluster that I've already shown you. And so what I would like you to note here is that this is constructed so that there is one palladium atom in the middle and the rest are all surface atoms. So basically we have no interstices here. So as long as we produce this, in theory, we should produce no interstitial hydride. And so it's just a little reminder that this is the topology of framework we opted for, because we knew that this has this 7.5 angstrom sized pore, which would be perfect to embed this kind of particle. Furthermore, we had previously shown that when the linker has an amino group on it, so while the crystal structure is identical, in the pristine framework, we don't embed the palladium particles in the pore. So you can see that larger nanoparticles are supported on the external surface of the framework. At the same time, when we have a functional group, the palladium particles are very small, so below 1 nanometer, and very well dispersed. So we decided to go with this particular composite. And so from the TEM, we saw that the particles were more or less the same size as we expected, so around 7 angstroms, but we also wanted to see what the average particle size was, and that we could do with EXAFs, and indeed it could be refined that the estimated average particle size is around 7 angstrom as well. So the local and the global probes are in quite good agreement. So we know that we've got this particle, which in theory should inform the interstitial hydride. So then we looked at whether indeed this is true. And the way we looked at it is, sorry, we used thermodesorption spectroscopy. So what we did, we actually used deuterium, but it doesn't really matter. So we loaded the empty framework and the palladium-laden framework separately with 100 millibars of deuterium at room temperature, and then quenched the sample temperature to 4K, at which point, well, first we allowed a half-an-hour equilibration before quenching, and so at which point the hydrogen should occupy all adsorption and absorption sites. And after that, we pump all the hydrogen that's not been absorbed or absorbed in the system, and we start to linearly increase the temperature, and we have a mass spectrometer attached to this, so we can see the evolving deuterium as it's being desorbed from the framework. So in yellow you see the empty framework, and in blue is the palladium-laden framework. And the first thing you can notice that here there is much more hydrogen coming off the empty framework, and that is good because that is the lowest. It corresponds to the lowest binding energy or adsorption entropy, if you wish. And of course, that should be the filling of the MOF pores. And we know that a lot of palladium is in there, so there is not so much room for the palladium, so for the hydrogen, sorry. Secondly, there is a little difference here as well. So still the empty framework results in the desorption of more hydrogen at around 80K. And we had previously assigned this desorption peak to desorption from the amino groups. And once again, because of the presence of the palladium particles, the amino groups are not quite as accessible for the hydrogen as in the empty framework. But perhaps the biggest difference is here. So you can see that above 200 Kelvin, no desorption event occurs from the empty framework. So we can assign this desorption to that from palladium. So this will be Chemisorption from palladium. And just to show you that if we have Chemisorption from palladium nanoparticles, it has actually a very characteristic shape, and the two different peaks corresponding to desorption from the alpha and beta phases. And as you can see, this is completely absent in here. We just have a big smudge, which already gave us confidence that the beta phase did not form, has not formed here. But we also carried out some inelastic neutron scattering. And just let me very briefly talk you through what you see here. In green, this is the palladium hydride spectrum in the relevant energy range. And in red, you have the spectrum of the palladium-laden amino UIO66 under hydrogen. And the black spectrum is a convolution of 3 different components, and this is a simulation we did. So on the one hand, we have this palladium hydride spectrum, which is exactly scaled to the amount of palladium that is present in the palladium-laden amino UIO66. We added this to the palladium-laden amino UIO66 framework in vacuum. And the third component is a kind of generic hydrogen in MOF spectrum, which we generated by measuring the spectrum of the empty amino UIO66 in vacuum and under hydrogen. And so we subtracted the former from the latter, from which we could generate a adsorbed hydrogen model. So by adding these 3 components up, we could generate a model a spectrum which should look like if all the palladium that was in the sample would form interstitial hydride. And as you can see, this is the peak maximum. And in the case of this simulated spectrum, indeed, there is a bump. So we should be able to see that. However, this is absent in the experimental spectrum. So this also confirms that we don't observe any interstitial hydride formation. So of course, that was the kind of the groundwork. And then we were looking at the actual catalyst performance. So we first checked whether it's active at all or not. And this is really just a quick test at room temperature. So at this point, the butadiene hydrogen mix is allowed on the sample, and we measure with a mass spec what's coming out of it. And as you can see, that the butene formation was imminent. We also looked at the selectivity as a function of time. And as you can see that it is really quite selective to the trans-2-butene formation. And there is only a very small fraction of butane that is formed. So the over-hydrogenation is really not that relevant here. So this is highly active, selective, and also quite stable. So previous catalysts for this reaction, palladium catalyst that is, tended to deactivate at a much shorter space of time than this. And we could attribute this stability also to that the palladium is always present in its metallic form rather than forming any hydride or potentially oxide. So far we've looked at really the catalyst and its atomistic structure and the chemistry, so the size effect as such on these particles. But particularly for heterogeneous catalytic reactions, it's not just the particle size that's of importance, or if you wish, the proportion of surface atoms, but also the kind of the chemistry or the chemical state of the surface atoms. So in order to look into this more in detail, we kind of stuck with the previous system. So you can see that this is still a palladium in amino U-66. And we were able to show that in this particular framework, there is a charge exchange between the palladium and the nitrogen of the amino group, so some kind of a charge transfer, which resulted in the a partial oxidation of the palladium and a partial reduction of the nitrogen. So we can see that there is some kind of a bonding between the two, and we could also kind of rationalize it in terms of a palladium nitrogen bond. Now, there is two things I kind of omitted previously. And the first thing is when I first mentioned or discussed briefly the usability of pair distribution function analysis. And I think I was a little bit hand-wavy when I said that as we subtract the total scattering data of the empty framework from the total scattering data of the guest-laden framework, you basically get to see the atomistic structure or the short-range order within the guest particles. So this is true, but not the whole of the truth, because we see everything that is not present in the empty framework. So we see the guests as well as any host-guest interactions. So what that means is that in such a case, we should be able to see palladium-nitrogen bonds in the pair distribution function data. And the other thing I would like you to recall is the thermal desorption spectra, where you could see perhaps a little dip in the hydrogen desorption of the amino groups. So of course, if the amino groups are bonded with the palladium, they will not be able to absorb hydrogen as well. So this is the real reason why the desorption of hydrogen from the amino group is much lower in the case of the palladium-laden framework. So then we did the same thing as before. We collected data on the empty and the palladium-laden framework, and we generated this difference curve from it. And once you can see in pink that this is very ordered. And the palladium short range order is in very good accord with the palladium bulk crystal structure. However, we have some additional peaks here which we cannot account for. And in particular, this peak here could be assigned to a palladium nitrogen bond. However, there was a little trick here, because we tried to rationalize this bond, this data set in terms of, so we've got our pore here, we've got the palladium in there, and so some of the surface palladium atoms will be or could be bonded with the nitrogen, but most of them wouldn't, because in any pore there are only so many amino groups. However, the intensity of this palladium nitrogen peak is quite high, so we were unable to rationalize the intensity in terms of the embedding of these nanoclusters inside the pores. And previously, we had hypothesized that in another framework, the amino groups may anchor single atoms of palladium rather than just allowing the palladium to fill the pores. So we took this hypothesis and we looked into it with different methods. I'm not going to go into all the details here, but this is an example I would like to show you because it kind of explains what we can see. This is inelastic neutron spectroscopy still, and if you're looking at the low energy range here, then what you can see in blue, so this is the spectrum of the empty framework, and in black you see the spectrum of the palladium radiant framework. And what you see essentially is what's happening when the palladium is added inside the pores of the framework. And what is accompanied by is the disappearance of loads of modes. In fact, many of them remain, which tells us that the framework is still intact, but many of the particularly the low energy modes, which can be associated with rotation modes, for example, disappear. So we looked at this with calculations a little bit more in detail. I'm going to zoom in here a little more, and I will also open this picture for you. So what I would like you to focus is really this bit here. So we've got a tetrahedral pore in this framework, and if we single out one corner, we've got three linkers around them. And the difference here is that obviously this is amino UIO66, so we've got one amino group on every single linker here. Now, normally, these linkers here are free to rotate, yeah? So this is a sigma bond here, this is a sigma bond here, so they can rotate like this. But it is possible that they rotate so that the amino groups for every single linker here are pointing inwards. And if it so happens, in particular when they're close to the corner, then they can pinch one palladium atom and immobilize it as a single naked neutral atom in here. And that is actually quite a strong bond, as it turns out, and that kind of fixates the structure as such, so the rotation becomes prohibited. And this is what we're actually finalizing at the moment for the phonon calculations. And this is relevant because this material in particular had been looked at for quite a number of catalytic reactions. And in particular, it's been looked at for CC coupling reactions, which we know that palladium single atoms are also active in, and it's never been hypothesized beforehand that the single atoms may be doing the job here. So there is actually maybe a significant amount of revision of this body of work that's needed. And just very briefly, I realized that I didn't have so much time left. I'm just going to briefly run through this, that since then we had been able to come up with a framework that only immobilizes these single naked neutral palladium atoms on it. And reassuringly, it wasn't active in carbon monoxide oxidation, so we don't have particles. it is somewhat active in the NOx reactions, but it's not particularly selective. So at the moment, we're looking at other reactions these could be explored for. And the final thing I wanted to mention is that although so far I've been mostly talking about how we can characterize the gas material itself and how the framework affects the gas material, it works the other way around as well. And often the addition of gas material changes slightly the framework, and the framework may participate in some catalytic reactions as well, in which case it has to be also examined on its own. And of course, one example is already what we just saw, how the rotation modes may be sort of fixated or blocked in a particular case. But the other example I want to show is perhaps a little bit more stunning, because normally we would be looking at the inorganic nodes, the clusters, as quite stable and unchangeable in a sense. And we found that when we add palladium to the amino UIO66, and particularly when we reduce it, and I would like to say that, so this is PDF data here, where we had already removed all the palladium contribution. So this is purely the inorganic, the interatomic distances in the inorganic nodes you see in red before and in blue after the addition and reduction of palladium. And what happens is that you can see that there is a shift. So this is just normalized. That's the difference between these two data sets. There is a shift in the zirconium oxygen and zirconium interatomic distances. And this is important because this may influence the electron density in these small nodes. So remember, these are hexanuclear, so they only contain 14 atoms in total, so including zirconium and oxygen. And this is a similar idea we'd find in the literature. So the changes are not maybe that stunning, but you can see perhaps the zirconium oxygen carbon angle is different, and perhaps more significantly, the zirconium oxygen bond length change as well. And this is obviously very important for acidity. And this is the last example I would like to give, because we had found that this may have an impact on the performance of a MOF-based catalyst. And this is related to methanol production and promoted copper. And I'm very sure that you all are very familiar with that. So I'm not going to go into a lot of detail. I can just tell you in advance that we didn't make much methanol. So you would be familiar that, of course, when you use zinc oxide promoter, then the activity is enhanced significantly. And also because it's a site selective reaction, there is a minimum of 8 nanometer particle size at which optimum activity is observed. Now, not so long ago, so 5 years ago, this group, Chamorier's group, looked into this quite interesting work. So they used the UIO66 framework, so this is with the terephthalic acid, and they used the 18 nanometer sized copper particle in 2 different ways. So on the one hand, they built core shell systems. So they built the MOF around the particle, the copper particle. And in the other case, they decorated the MOF particle surface with the copper nanoparticle. And they found that from just this difference of the copper versus MOF location, the performance was significantly different in the 2 cases. So both activity and selectivity were very different. So the MOF does somehow contribute to this reaction as well. And then this other work came out in which they kind of used the same topology, but they replaced the terephthalic acid by this bipyridinic dicarboxylate. So you can see the linker here, which what it does, it elongates the pore slightly, but the overall structure remains the same. And so when they sort of pinched zinc ions on the pyridinic nitrogens, that facilitated the assembly of copper nanoclusters inside the pores of the framework. And they found that this catalyst performed really well. However, there are two things that happened here. So on the one hand, the copper was nanoconfined. On the other hand, it also interacted with the zinc. So we don't quite know which one of this is more, which effect is more prevalent. And more recently, there has also been a work in which smallish copper particles were distributed and dispersed within the MOF particles. So they were still essentially like core shell type particles. So they're not sitting inside the pores, but the MOF framework is growing around a bunch of copper particles. And they found that, this is the Hiroshi Kitagawa group, and they found that the functional groups of the framework have an impact on the catalyst performance. So some questions still remain. So whether the nanocluster confinement effect in itself allows the retention of a good performance, or is electronic promotion necessary, and what the functional group's role really is. So we devised this very simple system in which we took UIO66, so pristine UIO66, and amino functionalized UIO66 as well. And we added copper nanoclusters inside the pores. In both cases, they were embedded in the pores. So to test if there is any strong interaction which could give rise to electronic promotion, we also looked at the chemical state of copper, and we saw that there was no oxidation. So in both cases, the binding energy was the same, and it also equaled that of the metallic copper. Now, copper is a little bit particular. So we also looked at the nitrogen binding energy to compare the nitrogen binding energy as observed in the empty framework with that as observed in the copper-laden framework, and it was exactly the same. So what you could see from there is that there is confinement effect, and there is no strong host-guest interaction, so we can exclude any kind of electronic promotion effect in this case. And more importantly, because the catalyst particle size is the same, the surface chemistry is the same, so any difference in the performance of these two materials or sort of matrices could come down to the presence of the amino groups in the framework. And what we found was the following. So I would tell you that neither of them were particularly good catalysts, which demonstrates that the nanoconfinement in itself is not enough to retain good catalyst activity. And indeed, we need to have the promotion effect as well. In the case, however, for the two materials, there was a significant change in the selectivity. Basically, the amino UIO66 matrix encompassing or embedding copper was not active at all. Whereas in the case of the pristine UIO66, we didn't observe a lot of methanol, but what we observed is that the methanol was sort of etherized, and there was a condensation reaction, and the main product was dimethyl ether. And that we could associate with the presence of the acid sites in the inorganic nodes of the UIO66. Now, the declaration of the presence of basic functional groups has a long-range effect on the nodes themselves as well, which had been previously suggested, and we could attribute that this has this detrimental impact on the amino UIO66, and therefore we don't see any significant catalytic activity in this case. So just to conclude, I hope I showed you the MOFs are a class of materials that are really quite interesting for controlling the geometry of nanocatalysts when we use them as templates and for the nanocatalyst growth. And the functional groups on the MOF linkers, but as I said, they can also potentially be added on the nodes may modulate the surface chemistry of gas nanocatalysts. And all of the above may be used to fine-tune the catalyst performance of these composites, and I show this a few examples of hydrogenation reactions. The guest inclusion, so this is mostly to show how the framework kind of fine-tunes the catalyst itself, modifies the catalyst itself, but in return, the catalyst guest may also modify the framework, and it can introduce strain effects. And this may have relevance to mass transport processes. So the example I showed you where the rotation of the linkers was blocked, we also observed that this was accompanied by an opening of the pore gates. And also we saw that there is some kind of a secondary contribution. So for example, through the suppression of acid character of the inorganic nodes. So with that, I would just like to thank my collaborators and students, as well as the funders, and thank you very much for your attention.
Excellent, and thank you so much for an amazing talk, Petra. I'm sure that I speak for everyone in attendance, and I'd like to take the opportunity that I've got for being the guy who introduces you to ask the first question. So I was very interested in this kind of idea of UiO 66 as a solid phase solvent, and how kind of the morphology of your nanoparticles, your palladium nanoparticles, affects selectivity of your reaction mechanism. Can you give some kind of overall idea of how much the nanoparticle, this solid state effect is overall important, and how much kind of other mass transport effects and say steric effects from the MOF itself affects catalysis?
So it's sorry for the what?
So is it as simple as to say that's okay if we can find, using gas phase calculations, that a nanoparticle of this morphology and this shape promotes this kind of reaction mechanism? Is that very transferable into saying that all we need to do is create a MOF that kind of promotes this?
I think that's actually the beauty of this kind of these frameworks, that it's probably not. So we do see that we significantly change the particularly the surface electron density in these frameworks. I didn't show all the samples we've made, but we are quite hot on looking at functional group effects. And depending on what group you add, you can really have huge oxidation, surface oxidation, partial surface oxidation effects on the gas catalyst. So there is a huge change, and if your reaction would the performance of your catalyst would depend on the promotion effects, then it would be very different. The catalyst performance for the catalyst embedded in the frameworks would be very different from the sort of naked freestanding ones.
Excellent.
And so I think there is the other thing, and yeah, I didn't go into a lot of detail, but so when we were first looking at the hydride formation, well, we assumed that it wouldn't form, but at the same time, because the interstitial hydride formation comes with an expansion of the lattice, so it is possible that it wouldn't form because the particles are so small, but it is also possible that the hydride doesn't form because there is this kind of straitjacketing effect as well. So that may contribute to that as well. So not necessarily, of course, hydrogenation reactions on palladium are very maybe sensitive to that, but in other reactions as well, you would have potentially some morphological change in the course of the reaction, and this straitjacketing effect may counter that. So is it good? Is it bad? I suppose that depends on the reaction, but I would assume that it would change as well.
Excellent. So we need to do the more high-level calculations and on top of the simpler ones. Okay, so I'm going to start by reading out of the Q&A. So Tachapan has also said, thank you for a wonderful talk. So I think everyone has the same opinion there. He says, I was wondering if you'd ever seen any evidence of defects in UiO2 materials. Would it be possible to have palladium at the defect site and may have catalytic activities different from palladium at the end sites?
Yes, this is a very good question, because of course UiOs in particular are very prone to defect formation. So we try to be very careful. So we try to do all the reactions at as mild conditions as possible. And also whenever possible, for example, when we do the PDF, we try to compare, sort of allow the empty framework to undergo the same treatment without the palladium, so we can maybe compare like to like as much as possible. But yeah, it's not something that you can exclude. Some things maybe give us confidence that it's not a huge extent in these samples. So for example, when we were looking at the particle size, so if we had defects, that's typically viewed as the major reason for larger particles to be present in the sample. So either you would have missing linkers, in which case two pores are sort of opened, or you could even have a node missing, in which case you can have really large pores present as well. And so then, of course, it's thermodynamically more stable for the particles to fill the larger spaces. So we would see we would see those filled. And although we had seen a couple of larger particles in the TEM, this is very rare. And we haven't really seen a lot of the crystallographic proofs of that either. So you would be able to point this real phase, which is the more defectful. So it's got a quite a characteristic diffraction peak. So we've not really seen that either. So I think, yes, there are, and I think they would have an effect, but that's probably the minor effect. But we could do maybe harsher conditions, in which case it may become more significant.
Excellent. So Lawrence also thanks you for an excellent talk. And she says, I was wondering if addition of an amine group in the linker affects the way of self-assembling process proceeds in the MOFs.
Yes, I wonder about this as well. Yes, very good question. Potentially, yes. If I can, this was one thing I was wondering, for example, in the case of this amino. I don't know if I'm still sharing, maybe?
Yes, you are, yes.
Okay, okay, very briefly trying to go back quickly. Sorry. Yeah, so in this case, yeah, so I was wondering is, for example, if a hydrogen bonding between the nitrogen, so sorry, let me restart a little bit. So let me start from here. So from a sort of functional group perspective, let's say, or a sort of entropy perspective, if you wish, if you have a functional group on the linker, so if you single out this corner here, then you can have two different positions because the rotation is allowed. So you could have the nitrogen up here. These would be sort of, let's say, crystallographically different positions, I suppose, or it would be down here if we view it from the perspective of this node here. And we see this happen when the three nitrogen, so three amino groups are near the corner. And I was wondering if, because we have three linkers, yeah, and we've got 4 nodes. So what are the chances that we would have at least 1 or 2 of these constellations, I suppose, of the amino groups around it? And I was wondering that indeed, as the framework is assembling, such arrangement would be preferred. So such arrangement, that is, all the amino groups are surrounding the corner because they can interact with themselves. But but then I think in that case, we wouldn't see much difference in the inelastic neutron scattering data, because for that very reason, because they interact, they would already, so the rotation would already be hindered. So in that case, probably not, but it is very possible that if you have larger groups, then simply they wouldn't, it wouldn't be possible for them to kind of surround the corner, or potentially that would already yield in some kind of blocking of the rotation. So, and yeah, maybe it would be then preferred that, for steric reasons, that they would be kind of alternating one up, one down as much as possible. So I don't know really, apart from doing this kind of really sort of scrupulous sort of vibration and rotational spectroscopy testing, how we could really see that. But I think it would be quite interesting, because it also may have quite relevant role in other phenomena.
Okay, yes, I see another question now, just popped into the Q&A. So Radha asks, what is the distribution of palladium nanoparticles throughout the UIO structure? Are they uniformly distributed? If they are distributed ununiformly, how does this impact mass transport of the substrates throughout the framework?
Yeah, so we haven't seen any sort of conglomeration at particular areas. So, sorry, first, you mean, I suppose the palladium particles are dispersed throughout the MOF particles rather than the size distribution. So we didn't really see any sort of conglomeration of particles. So we kind of assume that it's fairly random. I think in order to really tell that, we would need to do a proper MOF particle size dependent study. So try from really small MOF particles and try to make as large crystallites as possible, and do the same kind of testing through that. But we haven't done it yet. We've seen no evidence of it not being random. And at the same time, the loading itself is not that high. So in terms of weight percent, it would be typically below 5 weight percent. We have never been able to go above that. And because it's fairly randomly distributed, that we haven't seen any issues with mass transfer that wouldn't occur in the empty MOF otherwise anyway.
Excellent. I don't see any more questions unless I've missed something. I suppose while we're waiting, if I can be so bold as to ask one more. So I was also very interested in your talk of single atom catalysts. So on this ligand system that you produced, have you looked to see at what charge straits the kind of palladium is at? Is it kind of a cation, or is it purely atomistic at this moment?
Yeah, so it's not, so it's positively charged, but it's not a full, according to the XPS at least, it's not a full charge or oxidation number change. So yeah, so in the amino, so I think I didn't put it up here. Yeah, so here we had 0.7 electron volt difference. And I think, yeah, so an oxidation state change would for palladium would come about 1 or something like that. So it's, yeah, it's oxidized, but it's not fully oxidized. For the others, it's more oxidized, but it's still not. So we, for example, we did a sort of in situ exact study while reducing the precursor. And we definitely see, so we use a palladium 2 precursor added to the framework. So we looked at it and then we were ramping up the temperature, and we definitely see a change in the oxidation state as it gets reduced. So when I'm then looking at the XPS, I can see it's actually more oxidized than this. At the same time, the examples clearly indicates that it is reduced. So yeah, I don't know, Palladium 1, does that even exist? So yeah, possibly.
If I can just ask a B part to my question, what are the other reaction mechanisms that you're thinking of running with this catalyst? So I know you've seen CO oxidation and some hydride stuff. What's next to this one?
So we are looking at additional hydrogenation reactions at the moment. I think that's maybe that's established that they can be used for that. We are also looking a little bit at electrocatalysis as well at the moment, or we are going to, and yeah, I suppose, yeah. So one other thing that maybe I'm thinking about, but I haven't really convinced anyone of looking at just yet, is the CC coupling reactions for them. So I think, I know they're a bit messy, so maybe that is the reason why there is maybe less appetite for them, but perhaps with the simple work, with the system where we only have single atoms, that could be used as a kind of nice benchmark system to evaluate the previously published systems against, and really look at whether or not it's the cluster. So for example, in this case, we know we have clusters as well as single atoms. So then we would be able to tell which of them is active, or if both of them are active, then what's going on there. So yeah, so that's another thing that I would eventually like to look into.
Excellent. So we've got one more question in from Xiao Zhang. He says, "Hi Petra, thank you for an excellent talk," which I'm sure we all agree with. When we introduce the metal species into the pore, if we want to reduce the metallic phase, like platinum, palladium metal particles, is there a good way of controlling the metal particle size if possible?
Yeah, so so this is the idea that here it's the pore that controls it, and so let's say that limits it, and then through the functional group you potentially can go lower in size, but yeah, so the maximum size would come from the pore itself. Now, as I showed here, that it doesn't always work. So yeah, so in this case, so there has to be some kind of well, let me put it like this. So in the case of the palladium, but I think for many metals it's the same. We saw that copper likes to fit in everywhere, so it is happy in very small forms as well. So yeah, obviously you need to look at the thermodynamic stability of the and the surface energy of the individual metals. But in the case of palladium, it appears that it doesn't really like to get below 1.5 to 2 nanometers. So it's really it spills on the pores of pristine frameworks if that's above 2.5 nanometers, 2 nanometers easily. When it's below 1.5 nanometers, seems like some kind of a cutoff point. We could probably look at, probably in line with some kind of a magic number, I suppose, maybe 52 or something like that. And so below that, it's unstable. So we need to give a little extra help from the framework in that case. So in this case, we can do it by using the functional groups to help anchoring the particle itself in. So we know that in this case, we know what temperature the palladium nitrogen bond is broken. So one thing that I'd like to look at is that really heat treat it further and see if we can get rid of all the single atoms in that case while keeping the clusters. But yeah, this is something that we only recently found out, so I haven't done it yet.
The next stage. Okay, I see no more questions, so I think I will take this opportunity on behalf of everyone to thank you again so much, Petra, and maybe Corinne, you have an announcement or two?
Our next webinar will be catalyzing green hydrogen, which is on the 25th of November, and I will just pop the registration link in for that. And other than that, I'd just like to say thank you very much to Petra, and thank you for everyone for attending today, and of course to Matt for chairing. It's great.
Thank you very much for the invitation, the organization, and the chairing as well. Thank you.
Thank you very much.
Okay, I think we will end it there, but it's been an excellent presentation. I really hope that you will find some great collaboration in the hub, Petra, from all the interested participants.
Thank you, me too. Yeah, so yeah, you have my email address, I suppose.
I think, Corinne, you sent it around?
Yes, I'll just pop it in again now, yeah.
So if you're interested or have any further questions, please do not hesitate to email me. That's all. Excellent.
I think we will end it there, but thank you again. I can't say it too much for a very interesting and eye-opening talk.
Thanks very much.
Thank you. Bye.
Bye.